So consider the problem. You have got the graph of some function f of x between some initial x value and some final x value. So let's get a quick sketch going. This is my theme for the quarter. Let's get a quick sketch going. So here's just some arbitrary function f of x. Here is the initial a, here is the final b. And the goal now is not to find the area underneath the curve, but to find out the length of this string that's being used to actually form the curve. Now the idea here is pretty clever, I would say. The idea is pretty clever, and the idea is to try and segment this curve is a bunch of tiny little straight line segments. And if we subdivide those straight line segments small enough, it will be like a necklace made from chains, metal chains. It will be able to bend and move smoothly and approximate this curve quite well. Now, to find the length of each of these tiny line segments, we're going to end up using the derivative, which tells you the change in y as x is changing. So f prime of x, let's recall, is approximately equal to the change in y over the change in x. So let's take one of these little tiny line segments and let's try and figure out how long it is. So length of little segment. The length of every single little segment is given by Pythagorean theorem. If you take the square root of the little change in x, and the little change in y squared, then that square root will give you the length of this tiny diagonal segment on this chain. Now I can rewrite this ever so slightly by factoring out a copy of delta x. So delta y over delta x squared, factor a delta x and pull it outside of the square root, and that will bring you here. And if we let delta x get small, then we're going to get the square root of 1 plus f prime squared dx. So that is the length of this tiny little single segment on this chain forming the curve. To find the entire length of the full curve, we're going to use the integral to sum up all these little lengths. So to find the length of the arc formed by drawing the graph of f of x from a to b, all you have to do is integrate from a to b 1 plus f prime of x squared with respect to x. Just add it up and find the antiderivative, plug in the limits, and take the difference. Now please, this is the most important thing when you're working on these problems. If you are trying to simplify something like, I don't know, the square root of some quantity squared, let's call it u. Some quantity squared, let's call it v. If you think that this is equal to u plus v, you are going to have a hard time in this section. You're going to have a very hard time in this section. It is absolutely imperative that you remember that the square root of u squared plus v squared cannot be reduced to u plus v. These are not equal at all. Not equal at all. So with that in mind, let's do our level best to find the arc length of the graph of f of x equals 10 x to the 3 halves on the interval from 1 to 3. Our journey begins by finding the derivative of f of x. Using the power rule, 3 halves comes down and gives me 15 x to the power 1 half. 3/2, take away 1 to give me 1/2. So then I'm going to integrate from 1 to 3 the square root of 1 plus f of x quantity squared. Now, my job is to take the antiderivative of this without incorrectly simplifying the square root. So we have to be very careful here. Let's integrate from 1 to 3, the square root. Okay, let's see what happens if we work on this square here for a minute. 15 squared is 225, if I recall correctly. X to the 1/2 squared becomes x. So what I have is the square root of this linear function 1 plus 225x. This is a prime candidate to use substitution, with u equals 1 plus 225x, so that du is equal to 225 dx, so that 1 over 225 is equal to, times du is equal to dx. If I substitute that in, taking care to note that these are limits that are x values at the moment, then I will be integrating not the square root of 1 plus 225x, but the square root of u. And I can replace the dx with 1 over 225 du. Now, let's see how the limits of integration will also change. We don't want limits of integration in terms of x's, we want limits of integration in terms of u. If x is equal to 1, then u is equal to 1 plus 225 times 1, or 226. And if x is equal to 3, then u is equal to 1 plus 225 times 3, which is 676. So here is 226, here is 676 u limits. And now let's go ahead and find this antiderivative. 1 over 225 is unaffected by the constant multiple rule. Increase the power by 1, bring it back up to 3/2. Then divide by the power of 3/2 to counteract that power rule in reverse, and take the difference from the lower limit to the upper limit. So what would we have? We would have 2 over 675, and then we would have the difference 676 to the 3/2 minus 226 to the 3/2. That would be the final answer for this question: how long is the graph of the function between this starting value and this ending value? Now, if you're planning to take Calculus 3, I strongly recommend that you keep this formula in mind, because in Calculus 3, you begin to deal with quantities that are moving not just in a straight line, but perhaps in 2 or 3-dimensional pathways like this one. And you can use arc length to find the distance traveled by an object moving in a 2-dimensional pathway like this one. It's a very nice technique.